Okay. So an order written like this, less than or equal to, this is not your usual less than or equal to sign between, let's say.
Sir, a screen share is required, sir.
Sorry?
Share the screen, please.
Yeah?
The screen, you have to share the screen, sir.
Oh, goodness. You should have told me earlier.
Sorry.
Right. Well, anyway, I've just begun. So I have to
Thank you.
start sharing the screen. Here it is. I'm sorry. Can you see it now?
Yes, sir. It is
Yeah,
visible right now.
Okay.
Yes, sir.
Okay. Good. So let's recall the statement of Zorn's lemma. It's also called Zorn's theorem, and it's about ordered sets. Some statement about ordered sets. What is an ordered set? It's a set E with an order. And what is an order on a set? It is some relation between elements of this set E, which is reflexive. So I'm denoting it by this sign less than or equal to less than. I'll just read it as less than. Reflexive means that every x in E is less than x. That's true. That's the notion of reflexivity of any relation on a set. Then it should be transitive. So if x is less than y and y is less than z, then x should be less than z. So these two properties are shared with equivalence relations. But the third property is quite the opposite of what holds for equivalence relations. For equivalence relations, you want them to be symmetric. Whereas here, it's antisymmetric, which means that if x is less than y and y is less than x, then x should be equal to y. Okay? So some of the basic examples of this relation, of an order relation on a set, are of course the natural order relations on on the integers or rational numbers or real numbers. Okay. So here I did not require that any two elements of the set should be comparable. If that holds, which means that if given any two elements x and y, either x is less than y or y is less than x, then we say that the set is totally ordered. Sometimes an ordered set is called a partially ordered set. So a totally ordered set is one in which any two elements are comparable. And if I have a subset of an ordered set, S is a subset of E, E has an order, an element x of E will be called an upper bound for S if every element of S is less than this x. X is an upper bound for capital S if every little x in capital S is less than x. Okay? So these are just two definitions, ordered set, totally ordered set, and an upper bound for a subset of an ordered set. Now, an inductive set is one in which it's an ordered set, first of all, and it has some special property, which is that whenever I have a totally ordered subset, it has to have an upper bound, right? So obviously, if I take the set of natural numbers, and if I take any okay, so let's see. If I want every totally ordered subset to have an upper bound, right? Okay. So Zorn's theorem says that if I have an inductive set, right, then it has at least one maximal element. What is a maximal element? It's an element which doesn't mean that it's the largest element in the set, that every element of the set is smaller than this one. What it means is that if some element is larger than this M, then it has to be actually equal. There's no element which is larger. That's what maximal means. Okay. So this is the general set theoretic statement, which is useful in many other contexts. So I'm not going to go into the proof. We'll prove all statements about vector spaces that we come to, right? Okay. So before I can say what a vector space is, I need to say what a field is, right? So an element little x in a ring A is said to be invertible if there exists some y in A such that xy is equal to 1 and y times x is also equal to 1. This equal to sign here is superfluous, is spurious. It should be y times x, right? And a field is a ring which is not trivial, which is not reduced to the zero ring, and in which every element x, which is different from 0, is invertible. Okay? So, for example, I have the ring Z modulo nz. That's going to be a field if and only if this n is prime. Okay? So there's some checking to be done here. And other standard examples of fields, some of which you might be familiar with, are Q, R, and C. The field of rational numbers, real numbers, and complex numbers. There are also actually fields called QP and CP. For every prime P, you have a certain field called QP and CP, which I'm not defining today because I don't need them, but I just want to tell you that there are such things beyond the fields that you know. And then there's the field of rational functions with coefficients in any field, okay? And finally, there is this field. I have not required the field to be commutative. Usually, you make that assumption, but everything that I do today is going to be valid for any field which may or may not be commutative. For example, this field H of quaternions, some of you might be familiar with this, is also an example over which what we say is going to work. Now, a vector space over a field is just a module over that field. That's the definition. Okay, so it's not a new concept. If your ring happens to be a field, then that module is called a vector space. But what's really new in the case of fields is that every vector space has a basis. Over rings, we have seen that there are many modules which don't have bases. For example, this module Z modulo nz, it's considered as a module over Z. It doesn't have a basis, right? Because, for example, it doesn't have any free elements. I hope you recall the definition of a generating subset, a free subset, and a basis in a vector space, right? A basis is a free subset which also generates the module. Okay. So this is the theorem. We have to prove that every vector space has a basis. Now, this is actually going to be a corollary of this next statement, which is more precise, which is more, it's a more general result. It says that whenever I have a vector space E and a free subset L inside E, and a generating set S containing this free subset, right? Then there's a basis of E between containing the free subset and contained in the generating subset, right? So I'm given a vector space and a free subset of that vector space and a generating subset of the vector space containing the free subset. Then I can always find a basis which is between the free subset and the generating subset. So B has both the properties. It's free as well as it generates the vector space. Okay. So here is the proof. It says that if so, you take this German M to be the set of all free subsets of between L and S. So it's the set of all free subsets of the vector space which contain L and which are contained in S. And I'm going to define a relation of order, an order relation on this set M, which is just the inclusion of subsets. Okay, all the sets in M are subsets of the big vector space E, and some of them might be contained in others. So if A is contained in B, I say that A is smaller than B. That gives an order relation on the set M. Now we are going to prove that this M is actually an inductive set. Okay, so what do we have to show? That if I take a subset which is totally ordered, then I have to find an upper bound, right? This is what the definition of inductive set was. And every totally ordered subset has an upper bound. Okay. So here in this case, I'm given a totally ordered subset German N, and I have to find an upper bound in German M. So if I can show that the union of all these sets inside cap N, this union should have been certainly really called by given a different name, you know. This C is the union of all C inside N of the sets C. So it should have had a different name. This is, please ignore this for the moment. Let's just call it the union. Ignore this C equals this thing. So this union is in M. If it's an M, then of course it's an upper bound for this N, because every set in N is of course contained in the union. Okay, so what does it mean for a subset to belong to this German M? It has to be a free subset of S containing L. Of course, it contains L because each of the sets C in N contains L. And it's contained in S because it's each C is contained in S. So all that we need to show is that this union is actually a free subset of the vector space. Now for free subsets, we had proved earlier that a subset is free if and only if every finite subset is free. Okay, so take a finite subset D of this union, not C, that's not a good name. Take a finite subset D. Now, since this N is totally ordered, there is some N inside N of which D is a subset. Okay, that's because you look at the first D is a finite subset. So there are going to be finitely many sets inside which each element is going to be contained. And since they are contained in each other, there's going to be one which contains all of them. As this N is free, this subset D is also free. And our claim is established. Our claim was that this set is inductive, and that's now, that has been proved now. So what Zorn's lemma will imply is that it contains a maximal element. Let's call it B. So B is a maximal element in B, in M, which means that it's a free subset containing L, containing S, and there is no free subset containing L and containing S which contains B. That's what we have constructed. And now we are claiming that B is a basis. Okay, so this fact will follow from the following. So in order to show that it's a basis, what do we need to show? We need to show that it generates the vector space E, because it's already a free subset by definition. A basis is a free subset which generates the vector space. So we need to show that it generates the vector space E. Now, we know that E is generated by the set S. So if every element of S is in the vector space generated by B, then of course B will generate the whole vector space E. Okay, so that's what we need to show, that every element of S is in the vector space generated by the set B. Okay, that's what we have reduced to, and that's what this next lemma proves. So what does this lemma say? That if I have vector space E and a subset B which is free, and if I denote by F the subspace generated by B, and if I have an element X in E which is not in F, then the subset B union X is free. Why will this result imply what we want? That's exactly what we wanted, really, because you want to show that every element of S is in the subspace generated by B, and you take this X to be an element in S, and we will be. Then B union X will be free, but that's a contradiction because B is maximal. Okay, so this contradiction will show that every element of S is contained in the subspace generated by B. Okay, so let's prove this lemma now. We have to prove that this set is free. So suppose there is some linear relation between the elements of this set. So what will it look like? It looks like mu x plus the summation over all y in B of psi y B times y is equal to 0. These coefficients mu and psi y, these are elements of your field which are not given a name to. They are scalars. Now there are two cases. If mu is equal to 0, then I get a relation between the elements of y, which is not possible. The only relation is the trivial one, because by hypothesis B is a free subset. So if mu is 0, all these coefficients, all these scalars are 0. And of course, that means that there's no relation really. So what happens if mu is not 0? Because I'm in a field, mu is invertible. It's not 0, so it's invertible. And then I can write x as the summation over B, over y in B, of whatever you take mu to the other side and psi y to the other side. Then basically x can be written as a linear combination of elements of B. That would mean that x belongs to F, because F is the subspace generated by B. But that's a contradiction because we are told that X is not in F. So what does this contradiction imply? Contradiction says that mu cannot be non-zero, so it has to be 0. And if it is 0, then all the other scalars are also 0, which means that, the only linear relation between them is the trivial one, and therefore this is a free subset. Okay. So, my goodness, I'm running very late. Okay. So we come to the notion of the dimension of a vector space. First, we need a small lemma. So if I have a vector space which is generated by a single element B, non-zero element, non-zero vector, then it is a simple K module. What is a simple K module? Recall that it is a module which is not zero, but the only submodules are the zero submodule and the whole submodule. So a simple module is a module of length 1, if you remember what length of a module means, right? So why is a vector space, if it's generated by a single non-zero vector, a simple module? Because so in order to show that it's a simple, we have to show that every element in this, every non-zero element generates the whole subspace, whole space. So if I take this non-zero element A, it's going to be alpha times B with some non-zero alpha. And because and then I can write my B, the B was the given generator as alpha inverse A. So B is in the subspace generated by A, and therefore A generates the whole subspace, whole space. Okay. So now we come to this important fact, which we had, okay, so which we had proved only for vector spaces which have infinite dimension, but now here's the general case. So the theorem is that any two bases of a vector space are equipotent. They have the same number of elements. The indexing sets can be put in bijection. So if E has an infinite basis, we had already proved this earlier. I don't know, this number, page 45 is not there today. It was there last time. That was the last thing we did on Sunday. So let's assume that E has a finite basis, B1 to Bn, and let Ei be the subspace generated by B1 up to Bi. So I've got subspaces E1, E2 up to En. Here they are. 0 is contained in E1, which is contained in E2, etc., all the way up to En, which is equal to E, because this is a basis for E. Now, this sequence is actually a composition series for E. That's what follows from the lemma. What does it mean for it to be a composition series? It has to be a sequence, increasing sequence of submodules, starting from 0, ending at the whole space, and such that the successive quotients are simple modules. And what are the successive quotients here? The successive quotient here is generated by B1. The quotient here is generated by B2. E2 modulo E1 is generated by B2, and so on. And this lemma says that all these spaces generated by a single element are simple. So now the result follows from the Jordan-Hölder theorem, which says that if any two composition series for the same module have the same length, and actually the successive quotients are also isomorphic, but we just need the fact that they have the same length. So if I have another basis E1 to Em, that M will have to be equal to this N, and that's it, the base. So that common number of elements in a basis is called the dimension of a vector space, right? Here it is. So E is said to have a finite dimension if it is a finite basis, and the number of elements in that basis is called the dimension of E. So E is isomorphic to K to the M. K to the M, of course, is a vector space over K. So there is such an isomorphism if and only if M is equal to N, right? N is the dimension of E that's given to us. It's going to be isomorphic to K to the M, if and only if M and N are equal. So, and every generating subset has at least N elements. If it has N elements, then it has to be a basis. Similarly, every free subset has at most N elements. And if it has exactly N elements, then it has to be a basis. These are all consequences of these this theorem here, that between any free subset and a generating set containing it, there is a basis. And any two bases have the same number of elements. Okay, so if I take the direct sum of a certain number of modules, these are not modules now, vector spaces, then the dimension of the direct sum is the sum of the dimensions. That's because, you can get a basis of the direct sum by taking the disjoint union of bases of all the direct summands. Okay, here is a definition. If I take a subset S of E, then the rank of this subset is defined to be the dimension of the subspace generated by S. And the rank of a linear mapping between two vector spaces is defined to be the rank of the, or the dimension of the image of that mapping. Okay, now, so when I have a subspace F of a vector space E, the assumption is that F is a direct summand of E, and the dimension of E is the sum of the dimensions of F and the dimension of E modulo F. That's the proposition. And here's the proof. Why is E modulo F, why is F a direct summand of E? Basically because E modulo F is a free K module. We have just proved that every vector space has a basis. That's exactly what it means for having a basis, the same as being a free module. So E modulo F is a free K module. It has a basis. You choose a basis for E modulo F, and then and you choose elements of E indexed by the same indexing set as for the basis here. Then there's a unique linear map or linear section from E modulo F to E, taking that basis to those elements, taking each element of the basis to the corresponding element which you had chosen here. That is to say that this sequence splits. We have seen this kind of argument before, and the splitting of this exact sequence is equivalent to saying that F is a direct summand. And we have proved that when we have a short exact sequence like this, the length of the middle module is the sum of the lengths of the submodule and the quotient module. So that's what proves the proposition. And these lengths are being called dimensions here, right? Similarly, if we have an exact sequence of vector spaces like this, then the alternating sum of the dimensions is 0. This is a special case. Here you have a short exact sequence. This is an exact sequence of any length whatsoever. And this is also something that we had already proved for modules of finite length. We had proved that the alternating sum of the modules is of the lengths of the modules is 0. But here the length is being called the dimension. So this is really a special case of what we had proved earlier. Okay. So, yeah. Now, if I have two subspaces M and N, which have finite dimension, then M intersection N and M plus N also have finite dimension, and the sum of their dimensions is equal to the dimension of M plus the dimension of N. That's, again, a special case of something which we had proved for modules of finite length. So all that work that we had been doing for modules is not wasted, because we don't now have to prove these things about vector spaces. They are just special cases of things which we have already done. Okay. So what is the notion of a codimension? So I have a vector space E and a subspace M. The codimension of M in E, I have to say codimension in what? In E is really the dimension of the quotient, E modulo M. Okay? So if I have two subspaces which have finite codimension, then the intersection and their sum also have finite codimension, and the sum of those codimensions is equal to the codimension of M plus the codimension of N. Again, this is something which we had done for modules of for modules, and this is just a special case. Okay, here is something which is special for vector spaces. This is a statement that, so first I need to define what a hyperplane is. A subspace of codimension 1 is called a hyperplane, right? So the statement is that every subspace F is the intersection of the hyperplanes containing it. Okay? For example, 0 is the intersection of, it's contained in all hyperplanes. So the statement, one special case of the statement is that the intersection of all hyperplanes in a vector space is 0. Okay. So it's enough, actually, that would imply the statement also by applying it to the quotient, but let's look at this proof here. So what do we have to prove? We are given this subspace F, and if X is an element, is a vector outside F, then we have to find a hyperplane H which contains F but does not contain X. Okay? Here's how to do it. So what is given to us is that that F intersection Kx is 0. X doesn't belong to the subspace, so no multiple of it can belong to F. And that's what it means to say that the intersection here is 0. So as the intersection is 0, the sum F plus Kx is direct, right? A sum is direct. A sum of two submodules is direct if and only if the intersection is 0. Now this F plus Kx is, after all, a subspace of E, so it has a supplement. Every subspace is a direct summand, and a direct summand is one which has a supplement. So take a supplement N of F plus Kx. What it means, what a supplement means is that E is the direct sum of N and F plus Kx of these two subspaces, N on the one hand and F plus Kx on the other. Now let's look at this hyperplane n plus f. I have 3 vector spaces here. N plus f is also a vector space. Call it H. It's clearly a hyperplane, because it has a supplement kx, which is a line, which is to say that E modulo H is isomorphic to kx, which has dimension 1, which is to say that H has codimension 1, which is to say that it's a hyperplane. And I claim that this is a hyperplane which is required, right? I mean, that X doesn't belong to this H. That's clear, because this n plus f sum kx, that's a direct sum as well, right? So X doesn't belong to H, and f is contained in H, yes, because H is equal to n plus f. So every subspace in a vector space is the intersection of the hyperplanes containing that subspace. Okay. So let's come to the notion of the rank of a linear mapping. We have already defined it. It's the rank of a linear mapping U from a vector space E to a vector space F over the same field, of course, is by definition, that field is being called K here. So it's by definition the dimension over K of the image of U, which is also a vector space, right? And it can also be thought of as the codimension in E of the kernel of U, right? Because E modulo the kernel of U is actually the same, is canonically isomorphic to the image of U. So by what we have proved earlier, what do we get? We get these two relations. Rank of U plus the dimension of the kernel of U is equal to the dimension of E, because you have this exact sequence. The kernel of U is contained in E, and the quotient is equal to the image of U. Similarly, the rank of U plus the codimension in F of the co-kernel of U is equal to the dimension of F. That's because you have the exact sequence. Image of U contained in the vector space F, and the quotient is the co-kernel of U. So you have the short exact sequence, and from which you get this, this thing. So here is another way of thinking of when is U injective in terms of the rank of U. It's injective if and only if the rank of U is equal to the dimension of E. And it is surjective if and only if the rank of U is equal to the dimension of F. It's a mapping from linear mapping from E to F. So you see, for linear mappings between finite dimensional vector spaces of the same dimension, if E and F are the same dimension, then these 8 things are equivalent. What are the 8 things? That the mapping U is bijective, that it's injective. Why is bijective being equivalent to being injective? For example, it will follow from one of these relations, right? Injective means that the kernel of U is trivial, so the rank of U is equal to the dimension of E. Now you have to show that it's surjective. You have to show that the rank of U is equal to the dimension of F. But dimension of E is equal to the dimension of F, right? That's part of the hypothesis, and right. Okay, yeah, so here it's written here. So the so the equivalent conditions are that U is bijective, that it's injective, that's surjective, that is rank n equal to the dimension of the vector spaces, common dimension. It's also equivalent to U admitting a retraction. We have defined this notion of a retraction. It's a mapping from F to E such that when I first apply U and then that mapping R, I get back the identity mapping of E. Then the next condition is that U should admit a linear retraction. So I further require that retraction to be linear. Finally, U admits a section. That's a mapping from F to mapping S from F to E, such that when I first apply S and then apply U, I get the identity mapping of F. And finally, the requirement that U admits a linear section. So all these 8 conditions are equivalent for a linear mapping between vector spaces of the same dimension. Okay, so this is all we have to do about vector spaces today. And in the remaining 16 minutes, okay, so let me just try. I come back to, now let's come to the commutative situation. Till now, we had a ring which was not assumed to be commutative. In the first half today, we assumed that it was a field. But now let's assume that the ring, we are back to an arbitrary ring, but it's commutative. Okay? So an ideal in a ring can of course be considered as a module over itself, and an ideal is just a submodule of the A module A. So what it means is that if X and Y belong to I, then their sum belongs to I, and if X belongs to I and alpha belongs to A, then alpha times X belongs to I. So if I have an ideal, then of course I have the quotient module because it's a submodule in particular, and I have this projection of an A linear mapping from A to A modulo I. But this A modulo I can actually be made into a ring in a unique way, in such a way that this mapping pi becomes a homomorphism of rings. Okay? And that's kind of more or less obvious. How do you multiply 2 elements of A modulo I? So you already know how to add them, of course, because it's a module, right? So you just need to say how to multiply these any two elements. So elements of A modulo I will look like pi of X, pi of Y. I take 2 elements. And I can try to define their product, pi of X times pi of Y, as pi of X times Y. But before I can do it, I have to check that if pi of X is equal to pi of X prime and pi of Y is equal to pi of Y prime, then pi of XY is equal to pi of X prime Y prime. Now that is something that you are all capable of checking. So now we are assuming that this ring structure on A modulo I has been defined. Okay, and this construction, this quotient, has the following universal property, which is that if I have any mapping of rings F from A to B, which takes I to 0, under which the image of I is 0, then there's a unique mapping, this dotted arrow from A modulo I to B, which makes this triangle commute. Okay, there's a unique mapping G, it's called here, from A modulo I to B, such that this F is G composed with pi. Okay. And an ideal will be called maximal if there are no ideals between I and A. So, I had earlier defined a maximal element in an ordered set. Here also it's the same thing. The ordered set in question is the set of all ideals of A distinct from A but containing I. That is an ordered set, and any maximal element of that set, for the time being, I don't know whether such things exist or not, will be called a maximal ideal. So you can check that. I mean, we'll soon show that such maximal ideals. Oh, wait a moment. So, yeah, sorry. It's a maximal element of the set of all ideals of A distinct from A. That's all. So you can check that an ideal is maximal if and only if this ring A modulo I is a field. Okay, the ideal is distinct from A, so A modulo I is not the trivial ring, but you have to check that being maximal is the same as this being, the quotient being a field. Okay. So now I want to show that if the ring itself is not trivial, if the ring is trivial, if it's a zero ring, it cannot have a maximal ideal, right? For one thing, there are no ideals distinct from the whole ring, and a maximal ideal has to be distinct from the whole ring. So the assertion is that if the ring is not reduced to the zero ring, then it has a maximal ideal. Okay? So this will be a special case of the following theorem, which says that no matter which ideal of I of a ring A I take, provided that it's distinct from A, it's contained in a maximal ideal. Okay? So let's prove this assertion. So again, we make use of Zorn's lemma, which we began with. So consider the set of all ideals in A, which are distinct from A, and which contain I. That's a set. You order it by inclusion. So you say that an ideal J1 is smaller than an ideal J2 if J1 is contained in J2. So now the claim is that this is an inductive set, which amounts to showing that every totally ordered subset has an upper bound. Okay, so let's take a totally ordered subset N and take the union of all the ideals in this N. Okay, call this union U. So this is clearly an ideal containing I, because each J contains I, so the union contains I, and each J is an ideal, so U is an ideal. There's a small checking involved there, right? For example, if I take two elements X and Y in U, why is there some in U? Because I can find two ideals here, J1 and J2, such that X belongs to J1 and Y belongs to J2. And this set is totally ordered. So either J1 is contained in J2 or J2 is contained in J1. So we can, without loss of generality, assume that J1 is contained in J2. Then X and Y are both elements of J2 and J2 is an ideal. So J2 contains X plus Y, and therefore the union contains X plus Y because U contains J2. Right? So this kind of very small checkings you have to do. The important thing is that this ideal U is distinct from the whole ring A. That's because an ideal is equal to the whole ring if and only if it contains the element 1. Okay? Clearly, if it's equal to the whole ring, it contains 1. And if it contains 1, then it contains A times 1 for every A in the ring, which means that it contains the whole ring. So we just need to show that 1 does not belong to J, and that's because it doesn't belong to, no, we just need to show that 1 doesn't belong to U, that this U is distinct from the whole ring A. And that's true because 1 doesn't belong to any of the J's in N, because all these J's are ideals which are distinct from A. Therefore, this U is in my set M, which was a set of all ideals containing I, but distinct from A. And this U is clearly an upper bound for this set N. So by Zorn's lemma, this M contains a maximal element. And that maximal element is, of course, going to be a maximal ideal. So if I take a commutative ring A, which is not reduced to 0, then there's a surjective homomorphism from A to a field. That's the corollary of this proposition. It's a corollary because I just need to take K to be A modulo M, where M is the maximal ideal of this ring A. We have seen that if I have a maximal ideal, then the quotient is a field. Right. So why did I go into this thing? That's because I want to show that if I have a free module over a commutative ring A, then any two bases are equipotent. They have the same number of elements. Okay, so we had already proved this for arbitrary rings, not just commutative ones, earlier, but now we are proving. We have proved this for if the module has an infinite basis, right? But now we are proving it in general over a commutative ring. So, okay, maybe I should have said the ring is not reduced to 0 or something. Because I'm now taking a maximal ideal in this ring. Okay, if the ring is reduced to 0, the only modules over that ring is the 0 module, and there's nothing really to prove. So let's take a ring which is not the 0 ring. Then it has a maximal ideal. And the quotient little k of A modulo M, that's a German M, is a field because it's a maximal ideal. Now, this module E, which is given to me, inside it I can consider the submodule ME, which is generated by alpha times X, where alpha is an M and X is an E. Now that, and the quotient E modulo ME can be considered as a vector space over my field little k. So I need to multiply elements of this by elements of k. Elements of E modulo ME will look like A bar over B bar. No. Elements of k will look like A bar over B bar. A bar and B bar, where A and B are elements of the ring A. So I need to check that if I have the K module structure of E modulo ME is going to be defined by A bar, little a bar times little x bar being the bar of AX. But for that, I need to check that if I had A bar equal to B bar, then AX bar has to be equal to BX bar when I define them to be equal to the images of AX and BX respectively, right? And that's true because A minus B times X is in this submodule, modulo which I'm going. So this quotient module is canonically a vector space over this quotient ring, which happens to be a field. Okay. Now, to get the theorem, if I take a basis of E, and if I take the images in E modulo ME, it's enough to show that if I start with an A basis of E, then I get a K basis of E modulo ME. That will prove the theorem because over K, any two bases have to be equipotent. Okay? That's what we proved initially. We have already proved for vector spaces here. So, where is it? Here it is. Any two bases of a vector space are equipotent. So, we want to prove something similar for a commutative ring, that if I have a free module over a commutative ring and then any two bases are equipotent, I'm reducing that statement for commutative rings to a statement over fields. And that's the way to do it, by finding a maximal ideal in the commutative ring, going modulo that maximal ideal in the ring to get a field, and in the vector space, in the module, to get a vector space over that field. And this construction has the property that if I start with a basis of the A module E, then I get a basis of the K space, E modulo ME. Okay, so here's the checking that if E iota is a basis of E, then E iota bar is a basis of E modulo ME. So it's clear that this will be a generating family, and you have to check that it's free. And here's a small amount of checking which is required. And I'm already 1 minute over time. So let me quickly recall something that you might be familiar with, which is the theory of matrices over a commutative ring. So if I have a commutative ring, then this M, this boldface M, the set of matrices with little m rows and little n columns is denoted by this MNA. That's the notation. So matrices which have m rows and n columns, and the entries are from the ring A. And the elements of this free module A to the n, which are xi1 up to xi(n), these being scalars, are identified with this row vector, with this column vector, excuse me. It is n rows and just one column. So xi1 to xi(n), this vector here is, this vector space basically is being identified with the set of matrices with n rows and one column. And that is sort of, if that sort of comes with the identification of the morphisms or A-linear maps from A to E. From this set of A-linear maps to E, there's an A-linear map which sends U to U of 1, And that's an isomorphism of A modules. So in general, this set of linear maps from A to the N to A to the M is identified with a set of matrices with M rows and N columns. You see, the maps are from A to the N to A to the M, and the matrices have M rows and N columns. And what is the matrix associated with linear mapping F? F is being taken to the matrix. Here is the matrix, whose columns are the vectors to which F sends the basis vectors E1, E2, En of A to the N. A to the N comes with a natural basis, E1, E2 up to En, and F of E1, F of E2, F of En are vectors in A to the M, so they are sort of columns with M rows. So this here is a matrix with M rows and N columns. Okay, one of the things which you do with matrices is to multiply them. And one of the things which you do with linear mappings is to compose them. And the multiplication of matrices is defined precisely in order to be compatible with this composition of mappings. So if I have a linear mapping from A to the M to A to the N, followed by a linear mapping from A to the N to A to the P, then I get a linear mapping from A to the M to A to the P, right? This is G comma F going to G composed with F. Now this corresponds to a matrix here, this corresponds to a matrix here, and this corresponds to a matrix here. So the assertion is that these identifications are compatible with multiplication in the sense that the matrix of G composed with F is the matrix N times M. Okay, and in particular, you have this evaluation mapping. What is the evaluation mapping? It's here at the bottom. If I have a linear mapping from A to the N to A to the P, and if I have a vector in A to the N, then of course I can evaluate that mapping on that vector, F comma X going to F of X. Now we have identified this space of linear mappings with a set of matrices with P rows and N columns, and this free module AN with the set of matrices with N rows and 1 column. So when I multiply these things, I'll get a matrix with P rows and 1 column. Here it is. And when I evaluate, I get an element of A to the P. So the matrix, the column vector corresponding to the vector to the element Fx is actually the product Mx. Okay. Finally, there's this. I'll just take 2 more minutes. There's this notion of the change of basis. If you have a mapping between if you have a free module of rank n, and if you take 2 different bases, then you get 2 different identifications of M with A to the N. And if you have an endomorphism, or rather, let's first look at just the identity map from A to the M, from M to N, the identity map here. Then I have a basis here and a basis here, the B's and the C's, and so I can think of it as this identity map can be thought of as a linear map from A to the N to A to the N, sending the first basis to the second basis. Okay. But you are taking to define the change of basis matrix, you have to take the matrix of this linear map, the identity map, with Bi as the basis with Ci's as the basis in the first vector linear free module, and the basis B in the second module, right? It's the same module, but it has two different bases. So what I'm defining is the matrix of passage from the basis B to the basis C. There are two ways of thinking of this matrix. The first one is that I'm looking at the matrix in the basis B of the map which sends Bi to Ci. That's an endomorphism of the free module M. And in the basis B, it has a certain matrix. That's the matrix which is going to be called PBC, the matrix of passage from the basis B to the basis C. Another way to think of it is that I'm just taking the identity map between M and M, but I'm taking the matrix with respect to the basis C at the source and the matrix B at the target. Okay, so that's exactly what you can see, that they amount to the same thing. And finally, so this formula for the change of basis is this one. If I have an alinear, so if I have two vector spaces E and F and a linear mapping, okay, let's just talk about vector spaces. This works in great for free modules over commutative rings, but the idea is the same. So let's just talk about vector spaces. If I have two vector spaces of finite dimension E and F over the same field K, and have a linear mapping U between E and F, then I have two bases, E and E prime for E and F prime for F. Then I can take the matrix of U with respect to the basis E and F, or the basis E prime and F prime. So these two are related by this relation. Okay, where is the relation? I think I had not. Yeah, here it is. The commutative of this diagram is what is meant. So the matrix of U in the basis E prime F prime is going to be Q inverse the matrix in this basis times P. Okay, so that's when you are given a vector space and two bases at the source and two bases at the target and a linear map between them, then you have two matrices associated to this linear map. The matrix with respect to the first basis at the source of the target, and the matrix with respect to the second basis at the source of the target. So these two matrices for this linear map are related by, the one is P times the other times Q inverse if P and Q are the change of basis matrices. Okay, so I'll stop here today and see if there are any questions. Are there any questions? We don't really have much time, but maybe some quick questions if you have any. Yes? Yeah, hello. Dr. Gupta.
Oh.
Sanjay, yes.
Yes, I was just saying if there is no question, then let's thank the speaker.
Right, thank you. So,
Thank you.
I think there is small typo in last commutative diagram.
what?
U prime.
Tell me.
You mean U prime, right? U prime?
No, it's the same mapping. The mapping is the
Okay.
same.
Okay.
The point is, you have the same mapping U between E and F, but you have two different bases, E and E prime on the left, and F prime on the right. Right? So you'll have a matrix of U in the basis EF and the matrix of U in the basis E prime F prime. How are these two matrices related? They are related, so it follows from the commutative of this diagram. The matrix in the basis E prime to F prime, that's going to be, the order is perhaps, yeah, I mean, maybe it's P times the matrix times Q inverse or something, or it's the other way around, but it's important that the mapping U is the same here. U and U prime. It's not U and U prime, it's the same mapping U in both these places. Okay, right. So let's meet tomorrow.
Yes. Okay. Thanks.
Bye.
Yes, sir.
Yes.
Anyone?
Hello. Yeah, there was a question.
No, sir. No question.
Okay.